All right, everyone, good morning. So you're back with me for another week or so. And so we're going to be talking about today using crop canopy sensors for variable rate fertilizer management. I do want to tell you we're not going to be coding today, but I do have this presentation on the website as a PDF in case you want to, download it and take notes on that. So basically, already my website. If you go, all the way down, there is this link now for imagery-based VR nitrogen part 1. If you just open that, it's going to be a PDF that you can download and take notes if you wish. Okay, let's see here. All right, so I know maybe some of the undergraduate students in this class, if you were in the Principles of Precision Ag last semester, you may have seen a similar or a very similar presentation that I gave then. So bear with me, but this is going to be a good refresher if you've seen this already, and if you have not, let's go through this. So for today, here's what we're gonna cover. So basically, review within field variability, understand the different components of variable rate nitrogen management, understand the differences between variable rate algorithms. We're going to be talking about a couple of different algorithms and how we use them, how we choose which one we need. And then within that concept, we're going to learn about the high nitrogen reference and sufficiency index. Are two different things that are part of those algorithms, and we have to know what they are, what they do, why they're important. And then we're going to calculate variable rate nitrogen application, and then understand how all of these different components come together in a variable rate application case study. Okay, so this is something that I hope at this point in the class you've seen enough of this that this makes sense. But why variable rate, right? So why do we, and I mean, more broadly, not just talking about nitrogen, but why just variable rate of any sort of inputs? So this is just an example of a field where we have, where the authors measured pH. And so it was a gridded soil sampling campaign where you see like where the stars are or where the points were collected, and then they did interpolation. So we're all familiar with that process. But then here we see that the pH range of this field is ranging from 4.9 to 6.4. And if you are applying, lime or some other pH corrective amendment, if you just apply a fixed rate, you will be applying too much to the areas that already have high values. You're going to be applying too little to the areas that have low values if you go by the average of this field. So, we're really using variable rate to manage properly the need for variable inputs in a field and optimize both our crop response, but also decrease costs. Applying more where it's needed, applying less where it's not needed. So if you think of it, soil pH, at least, is something very, it's something that very static, right? It doesn't change as much from year to year. However, we also have crop vigor. So here I just have a map of a field that we're actually going to be using in our exercise on Wednesday. That is a crop vigor imagery. So this is a field, and we're seeing here green NDVI. So if you're not familiar with green NDVI, it's basically the same as NDVI, but instead of using the red band, we're using the green band. So we do see this variability in crop vigor, right? So wherever we see yellow colors is where is the most vigorous, and when we have like dark blue colors is where is the least vigorous. So if we come in this field and apply, let's say, nitrogen at the same rate, you will be applying more nitrogen to some areas than needed and less in areas than what's actually needed. So again, it's just different ways of us assessing variability. So one is with soil sampling, taking soil samples, sending into a lab and having a nutrient or a soil characteristic, in this case, or a pH. Another one is using a sensor like a satellite or a drone to give you an indication of crop vigor through a vegetation index. Okay, so if we think of it, there's really a couple of different types of variable rate management, depending on what you're trying to manage for. So we can think of it as stable, especially if we're talking about nutrients, right? So not seeding rate, not chemicals, pesticides, but just thinking about nutrients. There's really stable and unstable nutrients, right? So with stable nutrients are things that are normally immobile or really close to being immobile in the soil. Soil levels will change gradually over time. So it's not something that changes very fast and can be corrected or even built up with the effects of that application potentially lasting more than one growing season. Right. So if we think of it, what would be a stable nutrient? What would be an example of a stable nutrient? P and K. Yes, thanks, Arminder. That's right. So P and K are general examples of stable nutrients because you can apply them to the soil. You can even apply more than needed that growing season. They're still going to be available for the upcoming or for the following growing season as well. So P and K would be examples of stable nutrients. Biochar. So biochar, it's not the nutrient itself, right? It's more the amendment. So I mean, the way you can think of it is you could apply biochar for a given purpose, right? So we could apply biochar because you're trying to supply a specific nutrient, and then that specific nutrient is what we're thinking of, and not the source necessarily, right? Yeah. And then, in comparison, then we have unstable nutrients that are very mobile in the soil. Soil levels can change rapidly due to weather, fertilizer, crop uptake. Sometimes they may need to be applied every season. Well, they need to be applied every season and sometimes even more than once in that season. And can someone else help me with an example of an unstable nutrient? Nitrogen. Yes, thanks, Bo. Nitrogen would be an example here, right? So nitrogen has multiple pathways of loss. You can apply today, and if you have a heavy rainfall tomorrow, you may lose up to 60% of that nutrient just because you had an unfortunate timing of application and rainfall and heavy rainfall afterwards. So it's a very dynamic nutrient, very difficult to manage. You apply today, you hope it's going to be there tomorrow or for the next month or for the growing season, but you really don't know. And really, that is where sensors like crop canopy sensors like satellite or UAV are really helpful to assess those types of nutrients, like in this case, nitrogen. Okay, so
sorry, Dr. Bradford.
Yes.
I didn't get an example for unstable nutrient.
Yeah, so let's go through this slide here. I think that's going to help. And if it doesn't, let me know and I'll make sure to loop back around that. Is that okay?
Yeah.
Okay. So with nitrogen, there are three main pathways of loss of nitrogen. One of them is ammonia NH3 volatilization. The other one is nitrate NO3 leaching. And the other one is N2O nitrous oxide emissions. So if we think of it, nitrogen, once we apply nitrogen to the soil or to the environment, it is very dynamic. It undergoes multiple reactions and we're not going to get really into those reactions here, but more focusing on some of the potential products of those reactions, which can lead to losses. So in the case of ammonia volatilization, it basically happens when we apply urea-containing fertilizer on the soil surface, and that becomes prone to volatilization. There are some studies that have reported up to 60% of your nitrogen, urea-based nitrogen applied on the soil surface being lost as ammonia. That's a lot of nitrogen to be lost, right? And this I'm just, the average losses by ammonia is 18%, but I've just shown you the range of that as well. The next one that's also very important and perhaps very important for here in Georgia is nitrate leaching, right? So nitrate NO3 leaching can also be a very big portion of the applied fertilizer. and especially important in coarser texture soils. So when you apply nitrogen in any form, it will eventually be transformed to nitrate. There's no way to escape that. You will go through the nitrogen cycle and be in the nitrate form. Nitrate is a highly leachable nutrient or form of nutrient. Especially it is highly soluble in water. If you have a coarse texture, a sandy soil, and you get rainfall, especially if that rainfall is enough to move down the soil profile, that nitrate is going to be moving with that water. And when that movement goes past the root zone, that's when we consider a loss, because plants are not going to be able to recover that anymore. So that's basically what nitrate leaching is. And similarly, it can be a very important loss, up to 60% of applied fertilizer, depending on the timing that you apply and the timing and volume of rainfall in soil texture. Now, the last loss is nitrous oxide. So this, from a loss perspective, is not a major pathway of loss. On average, fields lose about 1% of the applied fertilizer as nitrous oxide. So it's not huge. However, for climate change purposes, it is a very important pathway of loss, because that is one of the greenhouse gases that are very important, and it's about 300 times stronger than CO2 in warming the atmosphere or warming the earth. So it's a really important gas when we're thinking more of like climate change. However, just from a farmer management perspective, is the one that is least important, because the proportion that is lost is very low. So, Peter, this is what makes nitrogen unstable, because we can apply today or tomorrow in hope that it's going to be there, that for when plants actually need it, and not be lost to the environment. And it is the one that is most dynamic, so undergoes the most number of reactions that ends up leading, some of them may end up leading to losses to the environment, which are all bad, right? If we lose nitrogen to the environment, the farmer is losing money because they apply the nitrogen, is not there for the plants to grow. The plants are probably not going to yield as much as their potential is, because now they're stressed because they don't have enough nitrogen, and we're hurting the environment, right? All these losses are important for the environment. And just to give you an idea, I don't know, maybe here in Georgia, we have some of this in some areas. I did my PhD in Nebraska, where Nebraska has like a third. So Nebraska is like the top 2 or 3 corn producer in the US. It has about a third of the state area is very sandy soil, and it has the most intensively irrigated agricultural area in the world. So if you look at a satellite imagery from Nebraska, you just see the rounds because of the pivots. It's just like highly irrigated. And so they grow lots of corn needs nitrogen, sandy soils, irrigation, perfect storm for nitrate leaching losses, right? So in Nebraska, where they have the perfect conditions for nitrate losses, they already have like policies that control what farmers can do, how much they can apply, what timing they can apply, because it is already a big issue. So those farming communities that are on those places of sandy soils, they already have the groundwater contaminated with nitrate to the point that they have to treat that water to drink. So I guess I'm not familiar with Georgia yet enough to know if that happens here as well, but this is just one way of like, it's not just with losing nitrogen, that's fine. I mean, it could become a very important public health and safety issue as well, in the case of nitrate in drinking water.
So, did you say that ammonia is also lost by leaching?
No, so ammonia is volatilized. It basically in a gaseous form.
So it's like nitrogen.
Yeah, so both ammonia and nitrous oxide are on the gaseous form. It's just that they happen in different places. So normally ammonia volatilization happens when you apply urea containing fertilizer on the soil surface. If you incorporate that fertilizer, ammonia volatilization losses are highly decreased. On the other hand, nitrous oxide happens mostly within the soil, right? Because you have to have anoxic conditions, or you create more nitrous oxide under anoxic conditions. So it has to be within the soil matrix. Yes, but you're right. Both ammonia and nitrous oxide are gas in the gas form. And nitrate is a solid, but is solubilized in water.
So then we have control.
Many ways we can control. I'm not going to get too much into that because that's not really where we're going. But yeah, that could be a whole course, controlling nitrogen losses. But we're going to talk about how to better manage, at least in this class, in this lecture. Okay, so nitrogen is one of the most limiting factors of yield for non-legume crops like corn and cotton. So if you ever worked with corn and cotton, and if you've ever seen a field that receives zero nitrogen, you're probably going to see that that is a very sad, low yielding field, because it's needing nitrogen. It's the most needed macronutrient that we manage in agricultural fields for crops that do not fix nitrogen. So, in Georgia, of course we have peanuts that we don't apply nitrogen, but cotton and corn are important crops as well. So we're applying, to get good yields, we have to apply nitrogen. However, we also have this other side that we may lose the nitrogen. So it's really something we have to think about, how to best manage that nutrient and still get good yields. Okay, so something that's also really interesting to think about is we're kind of talking about applying nitrogen at a fixed rate to a field sort of scenario yet. However, how much nitrogen is needed to maximize return varies within a field. So I just want to show you here a figure from a paper where they looked at that. So here we have, it is basically a map where we have each block here is depicting the best nitrogen rates that optimize return in that field. And this is one field, right? This entire strip is one field. And then the colors represent EONR. That's the economic optimum nitrogen rate. Here it is in kilograms of nitrogen per hectare, but you can think of this as pounds of N per acre. It would be pretty similar. So if you look at this field, imagine this is one field. Within this single field here, the nitrogen rate that optimize return range from 0 all the way to 280 within the same field, within the same season. That's huge variability, right? So even if you apply a fixed rate here, it would be very difficult for you to capture, you will never really fulfill the optimum rate for each part of the field if you apply just a fixed rate. So we need a lot of nitrogen for some crops. Nitrogen is highly, it can undergo different losses, and is also the nitrogen needed to optimize return varies greatly within a field. So how do we manage this? And you probably know where I'm going with this, with variable rate nitrogen management, right? So if we think of it, there are three components of variable rate nitrogen management. One is the sensor, the other one is the algorithm, and the other one is the variable rate equipment. So let's just go through each one of these and see what they are, what they do, and how they connect in the end. So let's begin by the sensor. So there are basically three different types of sensors we can use to manage nitrogen variably in space. The first one of them is basically an active sensor, and it is called active because it emits its own light source. If you think of it, all cameras, including your cell phones or satellites, most satellites are passive because they require external light sources. So if you use a satellite imagery to get NDVI for a field, that is probably using the sunlight as a light source. If you're taking a photo with your phone and you're not using the flash, you're also using external light sources. So those are all examples of passive. In this case here, the active sensor emits its own light source and then measures what's come back from that. Because it is relying on emitting its own light source, it has to be proximal. So it has to be closer to the plants. It's hard to have an active sensor that is too far from the plants, even though there are some examples. But normally for this purpose, they would probably be proximal. So very close to the plants. They can be used real time, right? So if you think of, you have a boom and you have multiple sensors that are measuring crop NDVI, for example, as your applicator is moving, it is measuring right there on the go the crop response, and maybe using that information to also apply variable rate nitrogen on the go as well. And data processing of that is pretty much automated because all the algorithms are already embedded in the system. It is sensing, processing in the algorithm, and applying. So some commercial examples of this would be Ag Leader, Optrix, and Green Seeker. So if you heard of those, that's what these most likely are. Now, another example of a sensor that we can use here is just drone or UAV, right? So those would most of the time be passive, so they rely on sunlight to collect data. They are remote because they are far from the target, so they're not proximal anymore as the active ones were. Normally, they work in a sense then treat, so they're not real time. So you go out to fly a drone, you have, you land it, download the data, process the data, make a map, and then you go back again and feed that map into a variable rate equipment. So they sensing and treating are not on the same path. And the data processing side is very intensive. If you've ever, well, I guess you guys just worked with UAV imagery actually. So that was the perfect connection there, because you did see, like, if you are a farmer and you have to do this on your own, it's a lot of work and it's very intensive. You have to know how to do things. So it's just more difficult, the data processing side. And then lastly, we have satellites, right? So satellites, most of them are still passive, so they do require sunlight to work. They are remote. They're the farthest away from the targets that we can use. They're also, in a sense, then treat style, because of course they cannot apply something for you. You have to use their data and then create a map and then feed that into a variable rate equipment. And data processing can also be intensive and require lots of know-how. So some examples here that we're going to be using in class include Planet and Sentinel. So Planet would be the most popular private provider of satellite imagery, and Sentinel, the public version of that, or the most popular public version of satellite imagery these days. Okay, now why do we use these sensors? How do they work? How can we use that information to understand what's going on with plants? So what we're seeing here is basically the spectral response of a plant. So we have wavelength in nanometers on the x-axis and reflectance on the y-axis. So if you think of it, what these sensors all measure is what is reflected back from reflected from them back into the sensor, right? So reflectance is what we're measuring, is what hits them and comes back. So this is the typical plant profile for using any type of light source that has wavelengths between 400 and 1,000 nanometers. So it's very typical that plants would reflect less on the visible range. So visible here would be from 400 to 700 nanometers. And here we have the bands of blue from 400 to 500, green to 500 to 600, and red from 600 to 700. And the reason why we see plants as green is because even though they're absorbing most of the radiation here on this range, green is still the one that has a little bit of a larger peak. So that's why we see plants as green. And the reason why plants absorb most of the radiation in this region is because they're using that for photosynthesis. That's the part of the spectrum they use to basically do photosynthesis and grow and develop. And then this rapid change here from the lower end of the red all the way up here top is what we call the red edge. So that is an important band for some of the sensors that we're going to use. And then after that, from 800 on is the near infrared. So near infrared here has a very high reflectance. So about, like in this case here on this graph, would be around 45% reflectance. And the reason for that is when plants are healthy, the leaves are healthy, they are reflecting a lot of the near infrared radiation. So we absorb a lot in the visible range because they are using that for photosynthesis. And if a plant is healthy, they reflect a lot on the near infrared. If a leaf is damaged, is perhaps, there is an insect feeding on the plant or damaging the leaf somehow, a disease or some other way, the near infrared would decrease because now it doesn't have as much of a structure, of a healthy structure to reflect, and is going to reflect less in the near infrared. Okay, now this is really important because all of these different sensors have different bands, and we have to know what they do and how they relate to plants So we can understand how we can combine those bands properly. So here's just a few examples. So the Optrix, which is the proximal sensor, has the bands red, red edge, and infrared. Sequoia, which is a sensor that goes on the EB drone. So Sequoia is the name of the sensor that goes on the drone. Has green, red, red edge, and infrared. And you can see the width being different here because that's how much information is being averaged within the band of that sensor. And that's also important. And then PlanetScope, which is one of the satellites from Planet, has blue, green, red, and near infrared. So notice here that PlanetScope does not have red edge, right? Whereas the other two examples I gave have, but it also has blue and the others don't. So this is just something important to keep in mind as we're selecting different sensors and want to use them for remote sensing. So different sensors have different bands, and even the same band will be the average of different wavelengths, right? So I guess here, if we look at the near infrared, we see that Sequoia is averaging a smaller part of the spectrum and calling that near infrared as compared to PlanetScope. So even though the name may be the same, they're going to say this is the near infrared band, it may be averaging different pieces of information. And just to keep in mind, right, bands are not created equally across different sensors. Now let's talk about why are these bands useful in agriculture? Like why do we talk about especially red, near infrared, red edge, and sometimes green as well? Why are they important? So I have here this figure I want to show you.
Sorry, Professor.
Yes.
Does it mean like if you say infrared in case of the good growth of the plant? So I see like the satellite is like giving much of these details. So is it better like to use the satellite rather than using the drone and the sensor or the active sensors?
Okay, so Dennis' question was about like if different sensors are averaging different amounts of wavelength and calling that a given band, is it better to use the one that averages the most? Is that kind of, yeah. It kind of depends. I mean, there's really not a good answer, right? I think that the extremes are easy to, or maybe one extreme is easy to say. Like if you think of our phones, right? Our phones are basically averaging. So if we come here, right? So our phones are really averaging most of this. So like 400 to 500, it's averaging calling that blue, right? So it's a very wide average. And when we're talking about plants, it's probably better to not be as wide. We want it to be more center and more concise. Well, how much is averaging for coming, especially from a multispectral sensor. Now, we're not really going to talk much about hyperspectral sensor, but hyperspectral would be the case where each 10 nanometers is a different band, right? So if you think here, you would have multiple bands within this blue region that a hyperspectral would give you. That, I mean, you cannot even call it by a name. You have to call it by, the center of that band, just because, you would have a lot of different bands just within blue. You cannot just call all of them blue, right? So it's really, I guess, related to the type of stress you're trying to assess and how specific that is. So with hyperspectral data, that imagine like a very small sliver of this would be a band, and they would have like hundreds of bands within where I'm just showing you 5. With hyperspectral, you can use those very, very detailed averages, small averages of bands to relate them more directly to something very specific. So let's say you can relate to a disease, or maybe to insect damage, or maybe to even specific gene or phenotype that plant is demonstrating. Whereas with when you have a lot of bands being averaged into one, you lose that resolution, right? It's harder to say, oh, this band here is related to stress resistance, drought resistance, let's say. But if you don't have that very narrow band and have an average, and that's just part of that average, it's harder to relate that way, right? So it is a balance, and I guess, and it's also a trade-off, because the more bands you have, the more expensive that sensor is. So you don't want to have hyperspectral for everything, even though if you have one, you could use it, but it's just the most expensive sensor to get. So the goal is to really understand what the main bands are, and then create sensors that have just those bands for that purpose. Okay, so how are these bands relating to crops, and why do we use that information? So here I'm just showing you a gradient of greenness on the, I think this is a given tree. So leaves from a tree that have different greenness levels. So if we look at number one here, it has about 700 milligrams per meter square of chlorophyll. So it's the one that has the most chlorophyll, that looks the healthiest. And then we just go down here, and number 20 is the one that has the least, right? So we can really see that number 20 has only 4 milligrams per meter square of chlorophyll. So we see this gradient of stress here. Now on this study, they went on each one of these leaves and used a hyperspectral sensor to see how that curve, the typical plant curve, will look like for each one of these leaves. And this is how it looks like. So if you think of it, this very healthy green leaf is the dark green leaf here that is at the bottom. So that, if you look here, so this is again reflectance and wavelength, and 400 to 700 right here. We see that the dark green leaf is actually absorb or reflecting very little in this region, because it is absorbing most of that. It is very healthy. It's doing a lot of photosynthesis. And also when we look at the near infrared, it peaks very high, right? Because it has a very good structure. It is reflecting a lot of that near infrared radiation. Now, on the other hand, the yellow leaf is on top here. So we see that from 400 to 700, the visible range where it would be absorbing to do photosynthesis is actually reflecting a lot of that, especially here on the green and red parts of the spectrum. And then when it comes to the near infrared, it is reflecting less than the healthy one, right? And so the way that we just connect those is that the visible region that goes from 400 to 700 is related to leaf pigment, and that could be chlorophyll, it could be other pigments that are normally related to crop being healthy and doing photosynthesis. The near infrared region that goes from 800 to 1200 nanometers is more related to leaf structure and biomass. So the more biomass you have, the healthier those leaves are, and the more intact they are, the more they reflect on the near infrared region. And if you think of it, we kind of need to know both of those pieces, right? I want to know how much biomass there is and how much chlorophyll there is in that biomass to really make an assumption of, okay, this crop is vigorous, is healthy or not. So we kind of need to combine both of those pieces of information as far as pigmentation and structure and biomass in one number. How can we do that? How can we combine band information into a number that relates them? Anyone has any guess? Emma, any thoughts? No. David, what do you think? Yes. Okay, so David said NDVI. That's right. I mean, NDVI is one of the ways, right? So NDVI is a vegetation index. So vegetation indices are how we would combine different bands into a number. Let's just go through some of them here. So the most common and is the one that David mentioned was NDVI. So NDVI stands for Normalized Difference Vegetation Index. It basically combines the near infrared number and the red number. So the near infrared and red bands is what are used in NDVI. NDVI is the most traditional. It's a great vegetation index. It's the most popular. It was the first one to be developed. However, it has some shortcomings, especially if you have high biomass crops, like cotton and corn are good examples of that. NDVI saturates because the red band saturates. So if you have a lot of pigmentation, the red band signal has a hard time differentiating good and really good when you have a lot of biomass and a lot of pigments. So NDVI, even though it's the most popular and the first option that people normally think of, it also has some shortcomings that can be addressed by using different bands. So the green NDVI is the same formula as NDVI. However, it uses the green band instead of the red. And the green band doesn't saturate like the red band. So it gives us back that power of differentiating good from really good crop canopies. Another popular one that people also use in ag is the NDRE, which is the Normalized Difference Red Edge. And again, is the same formula as NDVI. However, it replaces the red with the red edge band, which is that pink one where the quick spike happens here in this curve. So these would be probably the three most common ones that you're gonna see in ag. And if you're working in ag and somebody shows you an NDVI map and that's at a point on the crop growth cycle that already has lots of biomass, be suspicious of that because maybe that's not the best one to show the differences in crop vigor for that at that timing at least. Okay, so I'm just gonna walk you through kind of like using this example that we saw and how we would calculate, in this case, NDVI for these plants. So let's just go ahead and do the calculation. I mean, you don't have to do on paper, just, you know, as long as you follow with me and understand what we're doing, that's important. So if I need here the near infrared and the red bands, and let's first, so that would be basically the near infrared. This would be the red, right? Those are the regions we're looking at for NDVI. So if I want to calculate NDVI for, let's say, the dark green leaf first, I would take that value up there as being the near infrared. So let's say probably around 60% reflectance. And I would take this value here for the red, which is probably about, I don't know, very close to zero, maybe 2, 3, or 4% reflectance. And I would plug those numbers, right? So 60% minus 4, 60% plus 4, just do the math, and that gives us an NDVI of 0.87. So that's pretty much how we're combining these bands in this case here. If we were to do the same for non-calculated NDVI for the yellow leaf, the near infrared reflectance would be there, which is around 50%. The red reflectance would be around there, which is about 50% as well. So that, let's say 50 and 45%, we do the math and we would get a 0.05 value of NDVI. So we can really see how NDVI is very low for the yellow leaf, is very high for the dark green leaf. Okay, so we just talked about 3 vegetation indices, right? So NDVI, green NDVI, and NDRE, which uses red edge. So if we just think of it, the available bands in the sensor is what going to determine which vegetation indices you can calculate, right? So can we calculate all 3 VIs for all the sensors here? Or maybe can you think of one case where we cannot calculate a VI and tell me?
I think we cannot calculate green NDVI from crop threads.
That's awesome. Was that Kriti?
Yes.
Yes, that's right. Thanks, Kriti. That's right. So we cannot calculate green NDVI from Optrix because it does not have the green band. What's that?
NDRE from PlanetScope.
Yes, so Amrinder said we cannot calculate NDRE from PlanetScope. That's because it doesn't have the red edge band. That's right. So just for us to think about it, that even though I may want to say, oh, I want to use NDRE because that is more sensitive to different levels of crop vigor than NDVI, well, you need to check your sensor and make sure you have the proper bands to do that. Okay, so let's talk about algorithm now. So, I mean, in general, there are 2 different types of algorithms. One would be vegetation index specific, and in that case is normally built relating one vegetation index, so let's say NDVI, width and rates. So you go out to a field, you apply different nitrogen rates, and you come with a sensor and you measure the reflectance, calculate NDVI, for example, out of those different rates and relate those 2 things. So crop response to nitrogen with NDVI. It's normally also built with data that is collected in one specific state. So let's say you go, Georgia has its own algorithm, Florida has a different one, Kansas, Nebraska, Oklahoma all have different ones, which means that they may not work well when you go from one state to the other, right? So you cannot, normally they work best for the state they were developed, but if you try to use them outside of that state, it may not work as well. The flip side of that is a vegetation index non-specific algorithm. So it's built relating any normalized vegetation index with nitrogen rates. So it's not specific to a vegetation index. It is built based on the generalized response of yield to nitrogen. So if you think of it, if you ever, I mean, I don't know how much you've been around this, but let's say if you go out to a field and apply 0, 50, 100, 150 kilograms or pounds of N per acre, and you measure yield in the end, normally your response is going to be quadratic, right? So the first increments of nitrogen increase yield pretty fast, and then you reach a plateau after some point. So that's kind of that generalized response. And it's because it was not developed with those specificity of vegetation index and location, is more likely to work in other states or regions when you take them elsewhere. So I want to show here two examples of a vegetation index specific algorithm. So here we're seeing an algorithm from Missouri and one from Oklahoma, and I believe this is for cotton. And then, so we have NDVI on the x-axis, we have nitrogen rate that's being applied on the y-axis in pounds per acre. So we see here that under very low vegetation indices, it's not applying any nitrogen. Perhaps it's just assuming that it's so low that it's probably either not recoverable or it's just soil. And then once it reaches, I think here's probably around 0.3, both of them start applying nitrogen. The difference that the Missouri goes up and stays up all the way into a point, whereas the Oklahoma one goes up to about 40 pounds of N when NDVI is 0.3, and then increases gradually and decreases gradually as well. So if you think of it, if NDVI, if you were using these different algorithms for a field in Georgia and you measure NDVI being 0.6, you'll be applying about 83 pounds of N per acre if you use the Oklahoma algorithm, and you would be applying 100 pounds of N per acre if you're applying the Missouri algorithm. So we see that just the same data, just changing the algorithm is giving you a different nitrogen in response to that. Let's see here, how am I on time? If you have some time. Okay, so especially when we're talking about vegetation index specific algorithms, we have some issues, right? So let's say we just briefly talked that NDVI may not be the best when you have a lot of biomass, because it's not going to be able to differentiate when you get on the really good part of the crop canopy. So what if that is the case? And I say, you know what, NDVI is not the best condition here for me. I wish I could use green NDVI or maybe red edge. Well, if you're using a vegetation index specific algorithm like the ones I just showed you, I mean, there's nothing you can do. There is no algorithm for green NDVI in that case. Right. And again, I guess here there's a graph showing what I was telling you earlier of why NDVI using the red bands may not be the best case. So the red band saturates when we have a lot of biomass. We can kind of see like this, all the lines coming together here, the lines that were healthy, all the leaves I showed you earlier. So they saturate there. It's harder for the red band to give a different number of reflectance when crop is really good. And also here we have another example where we have LAI. So if you don't know what LAI is, it stands for leaf area index. If you think of it, if you look at a plant from above, how many leaves are stacked in a given area, that's what LAI means. So if you have a crop that you're looking above and it has 3 layers of leaves that are, I guess, intercepting each other, you would have an LAI of 3. This is basically what that is. So it's showing here to us that as green leaf area index is greater than 3, you kind of see this NDVI plateauing out, which is not good, right? Because if I have LAI of 6, it's not going to be able to tell me the difference between a 6 and a 4. And we do want to see this. So we want vegetation indices where this continues increasing linearly and does not plateau. So we have a better response. And that's what happens when we change the red for the green or red edge. So what if we need to use a different vegetation index and use a different band? Like, do we need a whole new algorithm? Yes, if you were using a vegetation index specific algorithm, like the ones I showed you from Missouri and Oklahoma. Okay, so another point here of why maybe that is not a good approach is what if, so we're using a vegetation index specific algorithm, but what if I have different growth stages? right? So here's just an example of some work done in Texas and Arkansas, where we have day of the year and NDVI, well, day of the year on the x-axis, NDVI on the y-axis, and just each line is a different field. And this is basically just showing the crop growing, right? So like you have lower vegetation or you have lower NDVI early because maybe crop wasn't even planted. And then it's planted, it starts to grow, it peaks, and then it starts to senesce and dies, right? So this is the typical response over time, over the growing season. Now, what if the algorithm that I'm using was developed at a specific growth stage? So in corn, let's say it was developed to apply nitrogen at V6, which is when the crop has 6 fully developed leaves. What if I go and use a different timing, right? The same algorithm. So if you look here, I'm just bringing this Texas example here a little bit bigger. So if you look at a given day of the year, NDVI here's probably around like 0.665 or so. If I go to a different date, the same crop, the same field is going to have a different reflect or different NDVI value. So what happens then if you are using the data for a different timing than what the algorithm was developed for? Can you still use it? Probably not. And then lastly, what if you have different varieties on the same field? I just want to show you here, maybe like if you haven't seen this, I think it's kind of cool to just appreciate that. So this picture I'm showing you here is the corn variety trial here in Georgia. So each plot that you're seeing there is a different variety. They all received the same amount of nitrogen. Even though they look different, if I were to tell you that this was all the same variety, you would probably think, at least I would think, that the difference in coloration is because of nitrogen. Some are more stressed than others, but that's not the case here. The difference in coloration is because they have different, each plot is a different variety. So that difference is coming because of variety effect, not because of nutrient deficiency effect. Right? So how can we build an algorithm that takes care of that addresses that difference for us and make sure that what we're seeing is actually nitrogen related and not variety related if you happen to have more than one variety in the same field? Let me see how we are on time. Okay, I think we can probably wrap up for now. We can stop here and I'll continue next class. Let me take your attendance before we head out. Let's just. All right, just submitted that. So we are gonna have next class, then we're just gonna wrap up the slides. I will have a quiz, so make sure you know what we talked about today. You understand what we did. You covered that because you're gonna need that for the quiz that we're gonna have next class. So I think that's all I had for today. If you have any questions, let me know. Maybe next class, the first hour, we're gonna finish this exercise here or finish this lecture. Maybe, I'll open up to see if anyone has any questions that you would like to discuss as a group about the project, the final project. And then we're gonna get into actually using drone imagery to do variable rate prescriptions. Variable rate nitrogen prescriptions next class. So thanks everyone. If you don't have any questions, I'll see you on Wednesday.